Okay, you have come a long way. You have learned a lot of things by this time of the course. To be honest with you, this course used to be taught in 2 semesters. There was a circuits course and there was a signal and system course. After a while, they decided to compress these 2 courses into 1 course. They make it a 4-hour course. Yes?
Did it alias?
I guess it must have alias with some of you. You must have alias with some of you. That's why you get rather confused. Okay. So let's recapitulate what we have learned so far in terms of Fourier series. So we learned about Fourier series that if a function is periodic, then if the period is t, okay, that you can expand this in terms of a Fourier series. Okay, where omega naught equals to 2 pi over t. That is the first thing you learn that is very interesting. And Mr. Fourier said this in the 1700s and early 1800s. Okay, and then we know how to find the coefficient. Coefficient is given by 1 over t over a period dt e to the minus j n omega naught t f of t. That was what we learned. Okay. Then we learned Fourier transform. Fourier transform is essentially obtained from Fourier series by letting t go to infinity. And if you do that, then this summation becomes an integral. You have the fact that any signal, not necessarily periodic anymore, can be written in terms of a Fourier transform integral f of omega. Okay, we learn about this and we derive the formula. And we also show you how to find f of omega. And that is given by minus infinity to infinity dt f of t e to the minus j omega t. Okay, so these 2 are derivable from each other. Then the next thing you learn is Laplace transform. And you can see that these are actually evolution of the same idea. Fourier series, Fourier transform, Laplace transform. And so far you have learned about this. That you only have learned how to do this. That given any function, I can always do this. And that is called the Laplace transform. It is actually very analogous to this. And I like to think of Laplace transform as a generalized Fourier transform. Generalized Fourier transform. Okay? So far we have not learned how to do the inverse Laplace transform. That is, given the Laplace transform, how do we find f of t? That we have not learned. But we can use all our prior knowledge to get that information. These are our prior knowledge. So if I give you this, how do I find this? Okay, that is called the inverse Laplace transform, which we are going to talk about in this lecture. You can think of the Laplace transform as a generalized form of Fourier transform. So if I write S is equal to sigma plus j omega, the Laplace transform looks very much like a Fourier transform. For instance, the left-hand side will become something like this, and then the right-hand side will become something like this. F of t e to the minus sigma t e to the minus j omega t. Okay? So you can think of the Laplace transform as a kind of Fourier transform, where given the signal you multiply by e to the minus sigma t and integrate. Why do you want to multiply by e to the minus sigma t? Why is that necessary? You want to make the integral always convergent. Okay? Laplace transform expand the kind of functions that you can take Laplace transform with. For instance, you can even take Laplace transform of an exponentially growing signal. This signal looks something like this, and it exponentially grows. And yet we can define the Laplace transform of it. If we multiply this function with this exponentially decaying part, so that the exponentially decaying part overrides the exponentially growing part. Okay, if we ensure that sigma is larger than a, you can even take the Laplace transform of an exponentially growing signal. Okay, but it actually is Fourier transform in disguise. Can you see this? It's Fourier transform in disguise. Let me write this down, since there are a lot of foreign students here. Okay, so given this, okay, you can actually do the inverse Fourier transform and say that ft e to the minus sigma t is actually equal to, if I apply this formula, which is the inversion formula that I have derived before over here, okay, is equal to 1 over 2 pi minus infinity to infinity d omega e to the minus j omega t f hat of sigma plus j omega. Can you see that? That is a true statement. I just invoke my knowledge of Fourier transform and find my f of t, but I do not find f of t directly. I find the product of f of t with e to the minus sigma t. Okay? Is this clear to everybody? Then I can write something that looks different from what I have and call it an inverse Laplace transform. And only if I could write this by taking this over to the other side, d omega e to the minus j.
C to the plus j.
Oh yeah, you're correct. When I take this over to the other side, it becomes e to the plus.
No. That is minus. In your inverse Fourier transform, that's plus j omega t.
Yeah, you're correct. You're correct. I have e to the plus j omega t. Always make sign errors. Okay? So this is very good. That actually saves my day. So I can write this as sigma plus j omega. I have this as my true statement. Okay? But when I integrate, I can actually convert this into a ds integration. I can call s is equal to sigma plus j omega. ds is equal to j d omega. Okay? And convert this into a ds integration. 1 over 2 pi. d omega is 1 over j ds. I put a j over here, I put a ds over here, and then I put a s in the exponent over here, and then I put back my s. Okay? And then the integration path becomes a little bit tricky. When I was integrating with respect to the real omega variable, this integration path is just on the real axis. Okay? But if I do change a variable such as this one, whatever that is real for omega, s becomes a complex number. Okay? So this integration path actually becomes sigma minus j infinity to sigma plus j infinity on the complex s plane. So if I were to draw the complex s plane, the integration path is something where I decide on what my sigma should be. Okay, this is the value of sigma, and this is my integration path. Can you see that? With this change of variables. If you have had a math course in complex variables, this is that soup. Okay, but if you do not have a course in complex variables, you might have to think a little bit as to what this means. Okay, you do a change of variables, and that is your Laplace transform. And this is the inverse Laplace transform. This piece over here. Okay, this piece over here. So it allows you to go from this to this and this backward. So it allows you to go from here to here and from here back to here. Okay? Actually, it's just a Fourier transform in disguise. Is this clear, or are there any questions? So how do we do inverse Laplace transform then? And as you have done in Fourier transform, finding these integrals are not easy. They're not easy. What you do then is actually, given a function, find what this is, and then given the function, find what this is, what do you do? What is the most popular method that you have learned to find Fourier inverse transform? Table lookups. Okay, table lookups. That is the easiest way. If you know higher mathematics, then you can do Cauchy integration theorem and all kinds of mathematical theorem to do those integration in closed form. Since you haven't taken the course in complex variables yet, table lookup is the easiest way to do the inverse Laplace transform. Okay? So, how do we do table lookups? Okay, how do we do table lookups? So, we try to find simple functions that we can do Laplace inverse transforms with. So we only deal with a special class of functions, co-rational functions. Say if I have the Laplace transform of something, and if I can write this as a polynomial in the numerator divided by a polynomial in the denominator, this is a polynomial. And this is a polynomial. Does everybody know what a polynomial is? Everybody knows, right? So everybody knows what a polynomial is, and you know what this means. Okay, this means that you might have something like a0 plus a1s plus a2s squared plus ansn. And then down below you might have b0 plus b1s plus b2s squared plus a polynomial of different order, bp, s of p perhaps. So this is called a polynomial, and this is called a rational function. Okay? We only learn how to find the Laplace inverse transforms of this class of functions. Okay, let's see how we do that. Then all of you know that polynomials can be factorized. That is, given a polynomial b0 s squared plus say bn, since the book uses n, I would use n, okay? That you can write this as s minus p1, s minus p2, s minus p3 times s minus pn with the maybe b sub n outside. Okay, all of you know this, right? Polynomials can be factorized. You do a simple example of what you have learned in high school, like b0 plus b1s plus p2s squared can be written as b2 s minus s1 s minus s2. We learned this in high school. Okay, if it's third order, there's no simple way to do it. If it's higher order, there's no simple way to do that. But all polynomials can be factorized. Okay, let's assume that this to be the fact. Then I can write this general function. I can also write a shorthand notation for this. which you might have learned somewhere. Okay, n is equal to 1 to capital N, s minus Pn, and then b sub n. Let me call this capital N. Let me call this capital N then. Capital N, to not confuse my index. So I can also write this as product of, this means the product of s minus Pn, and then when I put them side by side and multiply them together, I get the other function. Okay? So, if a function can be written as product of such a kind of function, in order to simplify this into something that you can use a table lookup for, you do what is known as partial fraction expansion. Partial fraction expansion, which means that if I have, say, a function that looks something like this, s minus P1, s minus P2, I don't have a table lookup for this function. Okay, this is maybe a simple example of a frequency response function. So what I do then is to try to break this up into A1 s minus P1 plus A2 s minus P2, and find A1 and A2, something that you have learned in high school. Okay? And if you have found this, you do a table lookup for this. S minus P1, what does the Fourier inverse or Laplace inverse transform to? What is that? Exponential function of some sort, right? Times a unit step function. So it's in your table lookup, so you know how to do each of these terms. Then the Laplace inverse transform of this can be done. Okay, so this is the general rule. So the most difficult part is perhaps the PFE. PFE, which stands for partial fraction expansion. Okay, partial fraction expansion. So much of this part of the course, or this section, is about partial fraction expansion. Okay? So how do we do partial fraction expansion? Something that you learn in high school, but we learn perhaps some more sophisticated technique. Say if we have Bs over s minus P1, s minus P2, dot dot dot, s minus Pn, okay? In principle, you can write this as K1 over s minus P1 plus K2 s minus P2 plus dot 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 plus Kn s minus Pn. Okay? How do we find K1, K2, and Kn? Think of the factorization is already provided for you. This factorization is not easy. We know how to factorize it when it's a quadratic polynomial. But when it's an n-order polynomial, we don't have a general rule. Okay? When it's quadratic, we know how to do that. It's as squared plus bs plus c, and then we can figure out the two roots, which is s is equal to minus b plus or minus b squared minus 4ac over 2a, right? Did I get this right? Okay, so the two roots are s1 or s2 are these two numbers. But in general, no simple formula exists. So let's assume that factorization is already done for you. So now the next task is to find the partial fraction expansion. How do we find K1, K2 to Kn? Linear algebra. That's too complicated.
Multiply by the denominator and then compare terms.
Very good. Okay? Very good. So Georgie got the idea. Say if I want to find K1, I just multiply the whole equation by s minus p1. If I multiply the whole equation by s minus p1, on the left-hand side, I will have vs over s minus, this should be 2, right? S minus p2, sorry. S minus p2 dot 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 s minus pn. Okay, that's what I get for the left-hand side. And then on the right-hand side, I have k1, and then I have k2 s minus p1, s minus p2, plus dot 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 plus kn s minus pn s minus pn, or p1. Now this equation, if I multiply everything by s minus p1, how would I find k1? Make it k1 immediately obvious or available. How can I find k1 given this equation? Do something clever so that k1 pops up immediately.
That s equals p1.
Same power.
Yes?
Look for the terms that have the same power as k1. Anything
Yes.
similar on the
Yes.
side?
Yes. Yes, how can I make all the other terms disappear on the right-hand side except for one term?
Make s equals p1.
Yes, yes, Yao Shu has the right idea. If I set s equal to p1, each of these terms will disappear, right? So, if I set s equals to p1, I only have k1 left on the right-hand side. Then, on the left-hand side, I just put p1 over here, and then p1 minus p2 dot 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 p1 minus pn. And that is my k1. How do I find my k2? I go through the same algorithm. Okay, you see the algorithm for it? Actually, you know the word algorithm, right? You know the meaning of algorithm. Do you know in one what algorithm means?
Step-by-step instructions. of how-
Step-by-step instruction in a procedure. Actually, this word came from the Islamic world. In Islamic world, you always put AL before a word to honor somebody. Okay? So this must have come from somebody with a name, and then you put an AL in front. You honor that person. Algorithm. Okay? You don't believe that?
No, he said algorithm.
At one time, the mathematics in the Islamic world is actually quite advanced, so we borrow some ideas from them, and we call those procedure of solving problem an algorithm. Okay? So this is an algorithm for finding K1. So to find K2, what do I do? S minus P2, and then set everything to S equal to P2, and then everything vanishes except for K2. And then you can find K1, K2, K3, and so on. So it's a very simple procedure. But the textbook calls it the thumbing procedure. I don't know why they call it thumbing procedure. Put your thumb over here, put your thumb over there, put your thumb over there. And then you have a way of figuring out what K1, K2, K3 is. But it's actually just this very simple procedure. You can read about the textbook method, which is called the thumb procedure. Okay, you cover something with the thumb, maybe you cover this with the thumb, cover this with the thumb, and then you see this equation popping up and so on. Okay? So what is the catch about this partial fraction expansion? What are the catch that you might encounter that doesn't work? When will this algorithm not work? The partial fraction algorithm. When can I write something like this? What assumption do I have to make about this rational function?
Decomposes into linear terms.
What is that?
Decomposes into linear terms.
Positive linear term? No. And if you look at this right-hand side, if I take this distraction away, if I look at the right-hand side, what happens to the right-hand side when s goes to infinity? When s is infinitely large? it goes to 0. Okay, am I guaranteed that the left-hand side will go to 0? And what kind of restriction I have to put on the left-hand side to ensure that the left-hand side also goes to 0 when s goes to infinity? The order of the polynomial below has to be higher than the order of the polynomial above, which means that, say, take an example, like I have a0 plus a1s plus a2s3, or s squared, okay? The denominator must be b0 plus b1s plus b2s squared plus b3s cubed. If we look at this polynomial, when s goes to infinity, okay, when s goes to infinity, how can I approximate the numerator? The numerator will become, which term becomes the largest when s goes to infinity? The s squared term becomes the largest, so in the numerator I can just write down this term, and then the denominator will be dominated by this term when s becomes very large. S cubed is always larger than, s squared is always larger than s, and so on. So the numerator, the denominator is that. And if I look at that now, do I see that it also vanishes when s goes to infinity? Okay, this is just equal to a to b3, 1 over s, right? It goes to 0 when s goes to infinity. So in order for this equation to make any sense, both of them must vanish when s goes to infinity. So you will need the order of this polynomial to be higher than the order of that polynomial. What it means is that if I were to write this in full as the polynomial form, a(n) as n, and then if I were to write this in full in the polynomial form plus b d s d, okay, I need b to be larger than n in order to be able to partial fraction in this manner. Otherwise, the two equations do not balance. Okay, this is rule number 1. So what do you do when that is not true? What do you do when the numerator has higher order than the denominator?
Yes, Professor Chu.
Ask me, okay?
Divide out a power.
Oh, divide out the power, that's very good, okay? Polynomials can be divided, just like integers, okay? Like if you have an integer but the numerator is larger than the denominator, you divide it out and get the remainder, just like 5 over 3. This is a fraction where the numerator is higher than the denominator, so you write this as that. Okay? And then this is a fraction where the numerator is smaller than the denominator. You can also do that in polynomials. Okay? You can also do that in polynomial. In fact, the Chinese have figured it out years ago. And there is something called the Chinese remainder theorem. And they use that to count things in the Chinese army called 韩信点兵. Okay? You know how to count that. And you use this polynomial theorem to come up with algorithm for counting soldiers. So, if you have this kind of thing, if the order of the polynomial in the numerator is higher than that of the denominator, you can always divide it out. Okay, say if I have a rational function, which is a, let me give an example of s plus s squared or 1 plus s. I cannot partial fraction this thing, but I can divide it out. I can do a long division, just like I had before. I multiply by 1 and get 1 plus s. I subtract the 2, I get s squared. Okay, I get s squared. and then multiply by s squared, I guess I get s squared plus s cubed. Does it make sense? No, it doesn't make sense. I get s squared plus 1. Okay? And then I subtract the 2, I have a remainder of 1. Do you all do this kind of division anymore?
Where is it?
I'm doing long division, but I apply to a polynomial. I multiply by 1, I get 1 plus s. I subtract the 2, I get s squared. I multiply by s, I get s squared plus 1 plus s. Sorry. And then I subtract, I get minus s. So my remainder is minus s. So this thing is equal to 1 plus s minus s over 1 plus s. Okay, there's a polynomial division. And now I can partial fraction the last term. Did I get it right? S squared s. S, I can still do one more division actually. I multiply by 1. Minus 1, I get minus s minus 1. So if I do that, I subtract the 2, I get plus 1. So I get s into plus 1 over 1 plus s. Okay, that's my answer. Yeah, that's the answer, right? So I get this one, which I can find is Laplace inverse transform by table lookup, and also can find the Laplace transform of this by table lookup. If I cannot, then I do a partial fraction on those. Okay, that is the algorithm for doing that. Okay, so in general, when the numerator is higher order than the denominator, do a polynomial division until you get a low order polynomial in the numerator, and you get something like this. Okay? What other hiccups can you run into in partial fractions? What are the hiccups that you may have? Okay, another possible hiccup is this, that what happens in this function you have R of s is equal to, say, 1 plus s into 1 plus s squared, 1 minus s. If you have a pole, these are called poles, okay? If you have a pole of multiplicity 2, you have to use a different rule for partial fraction. You will have to say k1, 1 plus s squared, plus k2, 1 plus s, plus k3, 1 minus s. This is the rule for partial fraction. The numerator is of lower order than the denominator, but I happen to have a pole. Poles are locations where the function goes to infinity. In that case, I have to write it in this fashion. Okay? Why do we have to write it in this fashion? You can actually think a little bit. What happens to Rs when s tends to minus 1? When s tends to minus 1, this term becomes 0. This term becomes 2. This term becomes, oh sorry, I shouldn't have 1 plus s in the numerator. Let me just say 1 plus 2s. That is better. Okay, that's better. And then when s is equal to minus 1, this is just minus 1. Okay, so approximately, when s tends to minus 1, I would have minus 1 in the numerator. Okay, and then I will have 1 plus s. This being very close to each other. This is 1 minus s. This is 2. Okay, so if you look at this function, it behaves like having a pole of multiplicity 2 when s is very close to minus 1. I can only balance this equation with a term like that. If I do not add that term in, the equation cannot be balanced, because the same behavior has to occur on both the left-hand side and the right-hand side. Because this is possible, I cannot exclude the fact that there should also be a pole of multiplicity 1. And then, of course, this one is to replicate this thing. So, in order to find k1, k2, and so on, what do I do? Well, I can multiply this whole equation by one plus s squared. Okay, I can do that 1 plus s squared, and then set s to minus 1 again. Okay, then I will have rs times 1 plus s squared, and then I will have k1 plus k2 1 plus s plus k3 1 plus s squared over 1 minus s, and then you set s to minus 1, and then you can get your k1. Okay, you can do the same thing for k2, and then you can do the same thing for k3. Okay, so these are the two hiccups that you run into, and let's do some examples. Example 11.6. How do we find the Fourier inverse transform? 11.16, you're given that h hat of s is equal to s over s squared plus 1. Okay? And you do a factorization of the numerator that all of us know how to do. A plus b, a minus b kind of factorization. This is a very simple factorization. You do a partial fraction. Okay, I will not go into the detail of doing the partial fraction. Plus, but if you do a partial fraction, you get this to be your answer. Okay? And we know how to find the Laplace inverse transform of this by table lookup. Then the Laplace transform of it, this plus this times the unit